All right, so this video is finishing up 11.1. Just going to kind of recap this definition here before we actually go into the problem. The definition is a sequence A sub n is called increasing if A sub n is less than A sub n plus 1, meaning that all current terms are less than the next term, or another way to say it, the next term is always bigger than the current term, in which case something would be increasing. Or you could say that it's decreasing if the current term is always greater than the next term, or the next term is always less than the current term. Therefore, the sequence would be decreasing. It's called monotonic if it's either increasing or decreasing. And I kind of like to add the word strictly there. So it's only ever increasing or only ever decreasing. It never changes direction. So that would be something which is called monotonic. The mono part being one, and the tonic, I'm not really sure, but it's monotonic. One way, one direction, something like that. I don't know. All right, so here's our example. The sequence 3 over n plus 5 is decreasing because, now there's a few ways that we can talk about this. This first way that I'm going to talk about is probably something that you've never really thought of or seen before. It's a way of doing a mathematical proof. Let me just show it to you, and then I'll try and explain it. So the idea is, based upon what we saw up in our definition, the next term has to be, in this case, less than the current term. Well, the current term, or the a sub n term, is 3 over n plus 5. So we're going to write 3 over n plus 5. And according to our definition, that has to be greater than the next term. Well, the next term is what you get when you substitute n plus 1 for n, because it's the next term. So n plus 1 represents the next term. Well, this will be a relatively easy one because the simplification is that 3 over n plus 5 is greater than 3 over, combining the like terms, you get n plus 6. And in general, we know that a greater denominator, assuming that the numerators are the same, a greater denominator means that it's a smaller fraction. So we can simply say, because the denominator is greater on the right. Okay, probably not a real official definition, but at least it gets you the idea of what it is. So by showing this, we have shown that this is a decreasing function because it holds true for every n and n plus 1, or every next term. And we showed that by simply plugging in the general term. So it's a way of doing proofs by using something in general, so something that would work for every possible n value. And remember, n, of course, is restricted to values that are whole numbers. Some of them that are not going to be necessarily so easy to figure out is when you have a variable numerator and denominator. So there are two ways to show that this a sub n equals n over n plus 1 is a decreasing sequence. Method 1 is like what we just did. So method 1, we need to show that the a sub n term is greater than the a sub n plus 1 term, or vice versa. We could show it either way. As a matter of fact, I'm going to turn this one around. I'm going to say that the next term is less than the current term. Same idea. So the next term would be plugging in n plus 1 for all the n's. So n plus 1 over n plus 1 squared plus 1 has to be less than the a sub n term, or the current term. All right, I'm going to take a little bit of simplification here. So we're going to have to FOIL the bottom. So that's going to give us n squared plus 2n plus 1. But that I also have to add the extra plus 1 from on the outside. So that's plus 2. Nothing I can really do on the right side just yet. In order to show this, I'm going to do a little bit of cross multiplication here. So really what you're doing is you're multiplying both sides by the common denominator, but the common denominator is both denominators multiplied together. We don't want to FOIL all that out. There's no reason to do that just yet. But I'm going to multiply the top and bottom of the left-hand side by the common denominator, which is really going to give us n squared plus 1 times n plus 1. And it has to be less than, I'm going to do the same thing to the right side, so that's going to give us n times n squared plus 2n plus 2. So it's basically cross multiplication. All right, so let's go ahead and FOIL these things or distribute them out. So on the left-hand side, we're going to get n cubed. Let's see, we're going to get plus n squared plus n plus 1. On the right-hand side, we're going to get n cubed plus 2n squared plus 2n. So what I'm going to get, let's see, I can subtract n cubed on both sides. Those are going to go away. I can subtract n squared and n on both sides. If I subtract n squared and n on both sides, that's going to leave me with a 1 on the left. And let's see, n squared subtracted from the 2n squared gives you n squared. 2n minus n gives you n. Remember that n is restricted to whole numbers, so 1 is always going to be less than n squared plus 1, no matter what. And since that I have shown that this is an always true statement, a sub n is decreasing. Because we started off with the assumption that it's a decreasing function, and then a decreasing sequence, excuse me, and then we plugged everything in to show it, and we simplified it to a statement which is always true. So we have shown decreasing. Maybe that one doesn't make as much sense, or maybe it doesn't make as much sense to you, is what I'm trying to say. But this other one might make much more sense because it's based more upon the calculus that we've been doing. So if instead we let our function f of x equal the a sub n as if it was a function, so that would be x over x squared plus 1, well, how do we show that a function is decreasing? We would take its derivative and show that the derivative is less than 0. Same concept. So let's take the derivative. This is going to be a quotient rule, so derivative of the top is 1 times the bottom minus the derivative of the bottom, which is 2x times the top, over the bottom squared. So there's your derivative. What we want to show is we want to show that this is less than 0. So technically, you could multiply both sides by the x squared plus 1 squared, and you'd still have 0 on the right-hand side. But if you think about it, you want to make sure that that doesn't actually affect your function before you do that. I've got x plus 1, excuse me, x squared plus 1 squared. No matter what x value I plug in, remember the x's are going to mirror your n's, so they're going to be whole numbers. But no matter what x value I plug in, as long as it's a whole number, that will be no less than a positive number ever. X squared is going to give you a positive, plus 1 is still positive, and then if you square it, it's still positive. So that will not affect the function being negative. So really, I'm just going to get rid of it. I'm not really getting rid of it. I'm really kind of eliminating it from our purposes here. But again, you could multiply both sides by that. You'd still get rid of it. So then let's see, we'd have, let's see, our x squared plus 1 minus 2x squared. We want that to be less than 0. So combining our terms here, we are going to get, let's see, 1 minus x squared is less than 0. If you were to add x squared to both sides, you get 1 is less than x squared. Turning that around just to make it look a little bit easier, x squared then is greater than 1. So that means that the absolute value of x must be greater than 1. Now again, we're only considering n values of whole numbers. So technically I don't really need the absolute value. For the function itself you would. But basically what that's saying is for any n value greater than 1, this is a decreasing function. So for n greater than 1, a sub n is decreasing. And that's how you might go about showing that a function, excuse me, a sequence, I keep saying function, a sequence is decreasing. All right, we've got one more concept that I'm going to talk about here on the next page. I am actually not going to do the last page because it's neat stuff, but it's not worth our time right now. So the definition is a sequence is bounded above if there is a number m, just some number, such that a sub n is less than or equal to all those values. So in other words, is there a number above that we will never get bigger than? All the values in the sequence cannot pass that number. That's what it means to be bounded above. To be bounded below, just the opposite idea. In this case, we called it lowercase m. It just means that that has to be the bottommost number that you can't go past. Doesn't mean that you will necessarily hit it, but you can't go past it. And then something is considered bounded above and below. It's called a bounded sequence. So you could be just bounded above, you could be just bounded below, or you could be bounded both ways. And if so, it is just called a bounded sequence. So let's go ahead and look at this example. The sequence a sub n equals n. So literally the sequence is just defined by n. Is bounded below. Because if you think about it, a sub 1 is 1, a sub 2 is 2, a sub 3 is 3, and so on. There is no value less than 1 that we can use. However, it is not bounded above. But not above, because that's going to go on forever. 1, 2, 3, 4, 5, 6. It's going to be infinite. It's going to keep on going. It would be bounded below, but not above. 1 is the smallest possible value, infinite numbers above, so there's no bound. The sequence n over n plus 1, which we've done before, is what is called a bounded sequence. And that's because if you plug in 1, you see you would get 1 over 2, or 1/2. And then if you plug in infinitely large numbers, remember that this one has a bound above. It'll never get there, but it is bounded by 1. It will never get to 1. We saw that one graphically. So it's called just simply bounded. Okay, we can find a lowest and a highest possible value that it will never get to. Well, the one it will never get to, the 1/2 it did get to. Not all bounded sequences are convergent. Okay, in the second case, we know that a sub n, n over n plus 1, that was convergent. It converged to 1. The first example that we did, a sub n equals n, that's not convergent at all. It diverges, it just keeps getting bigger and bigger and bigger. But not all bounded sequences are convergent. You can have a bounded sequence that is not convergent. And we've seen this one as well. A sub n equals -1 to the n. That was the sequence where it looks like this. And so on. It just keeps bouncing back and forth between -1 and 1. It's bounded. It's bounded below by -1. It's bounded above by +1. But that's a divergent sequence. So it is bounded both above and below, so we just call it bounded, but it is divergent. So just because it's bounded does not mean it has to be a convergent sequence. So there's a case where that would be the bounded but divergent. And then we have this thing which is called the monotonic sequence theorem. Again, monotonic means that it goes one way. It's either always increasing or always decreasing. Every bounded monotonic sequence is convergent. Now think about that. It's telling you that it is bounded above and below, and it's always either increasing or decreasing because it's monotonic. If something is bounded and it's always moving towards that bound, that means it's going to be convergent because it will converge to that bound. Okay, really kind of not the easiest thing to state unless it just makes sense to you. But again, if it's got a bound above and below and it's always moving in one direction because it can't pass the bound, it's going to approach the bound. So it would be convergent. So a sequence which is strictly increasing or decreasing and bounded is always convergent. All right, that's all we're going to do. Again, I'm not going to do the last page in this case. It's a pretty cool thing to look at, but at the same time, it's just not worth our time at this point. So that should cover it.